Good morning, Stephen, or I suppose good afternoon for you in Zurich.
Exactly.
Welcome.
Morning.
Would you just like to say a few words about yourself, your position, etc.?
Yeah, so my name's Stephen Ferguson. I'm a professor for biomechanics at the ETH Zurich. I've been a full professor of biomechanics for almost 10 years now. And previously, I was at the University of Bern and did my formal education as a mechanical engineer in Canada. And my group really looks into several aspects of musculoskeletal health, all the way from basic science through to translation, medical device development, and new biomaterials applications. So we're quite broad in our treatment of musculoskeletal health and the problems associated with that.
And does it tend to be kind of challenge-based research? So you pick a particular topic, or is it more around, or is it a mixture of that with kind of more fundamental kind of aspects?
I'd say both. So I bring from my own background and general curiosity the more basic science and exploratory nature. So just as an example, I've always had an interest in soft tissue biomechanics. And so I keep a small parallel stream of simulation related research going on to explore the behavior of biological tissues under the effect of mechanical loading, and we'll keep doing this. But through our collaborations with the orthopedic clinics in and around Zurich, we always have also topics pushed to us by the surgeons. So what are the fundamental problems in the clinic that they would like to see solved in the next couple of years? And that's where we also do very applied research. So it could be the improvement of the delivery methods for a biomaterial or enhancing the mechanical properties of some materials to get a better performance in the implant. So we're really coming at it from both sides of the coin.
Okay. So kind of one of the activities you've been engaged with is kind of lifelong joints between 2013 and 2018.
Yes.
We did a lot of work with Professor Redmond from Leeds Teaching Hospital Trusts around the biomechanics of the hip.
Mm-hmm.
And you published a paper recently, Lund et al., which which talks about the application of this data to standards. Could you just provide a bit of background to the paper and why you think that paper is important?
So we found this a really interesting collaboration, and it kind of grew organically over the course of the Lifelong Joints project. So in Tony Redmond's group, he has a lab which is situated between sort of the technical sciences in Leeds and the clinic, where they do motion analysis of human subjects, both healthy volunteers and patients. And we were coming into the collaboration with a background in musculoskeletal simulation. So it's making simulation models to predict the forces within the joints of the body in a variety of activities. And the two groups really came together with Redmond's group providing motion analysis or motion measurements of over 150 patients with hip prostheses. And we then took those data sets and simulated the joint loading for each of those individual cases to see if there were some special characteristics of an individual patient or the way they moved that would influence the loading of their joints. And the final outcome of this was that we could stratify the patient groups in terms of, for example, their body mass index, the speed with which they walked, the level of their clinical outcome, and see if there were distinguishing features in the way they loaded their hip joint that could be linked back to some of the factors that were used to kind of categorize them. And the final outcome was that the way people moved really has a substantial impact on the loads that are applied to a joint, and that these loads are not necessarily what is typically understood to be the average normal loading of the hip joint.
Mm-hmm. Okay, thank you. Thank you. And part of this was you made a challenge, didn't you? Implicit in the paper was that standards are important documents. Mm-hmm. But one of the things that you suggested was that they take into account these kind of different loads or these different kind of motions because they do impact on, let's say, the wear of the joint. Mm-hmm. Could you just explain that in a bit more detail, including, why standards, kind of where standards are used and why are they important?
Sure. And I think we're not, of course, the only ones to have mentioned this. I can point also to the group of Georg Bergmann, who was a pioneer in the in vivo measurement of joint loading. So for over 20 years, his group had put instrumented implants into the bodies of patients to measure joint loading. And he makes a similar proposal that the loading profiles which are used in the definitions of standards for testing implants in a preclinical environment, these are generally arrived at by consensus of a panel of experts in the field. But of course, it's usually this consensus is developing a best case scenario or most applicable scenario for testing standards that could be applied in a lab with a reasonable amount of effort. And if you look at what's then defined in these standards, the loading profiles are kind of an averaged or distillation of scientific investigation over the past 20 years, where joint loads are quite often analytically calculated and present a rather idealized smooth curve of how much force is going into the joint and how does it move. If you then compare those standards dictated loading and motion profiles against what we saw in the actual patient measurements in terms of motion and what we then calculated from our musculoskeletal modeling in terms of joint loading, they tend to digress quite wildly in some cases. And the same is also observed in the in vivo measurements from Bergmann's group, that there are sometimes perturbations or special cases in motion, like someone stumbling or running more quickly or slowly up a stair, that can deviate outside the envelope of the prescribed forces and motions that are accepted in the standards. So at the end, what we then said in this paper and the challenge that we present is, yes, the standards present a nice starting point to do kind of a time averaged simulation of how a joint is loaded, but doesn't capture some of the special loading cases which may actually be most responsible for poor performance of implants.
Yeah, and that was certainly the case in the metal on metal debacle in the 2000s, where we had edge loading, kind of a misalignment of the prosthesis, and that led to an increase in the release of particulate debris of nanometer size. And there are standards now. There is a standard, I think I'm not quite sure which number it is, but there is a standard now that looks at kind of edge loading for hip replacement. But again, it's been, it's a reflective development rather than a kind of prescribed development.
And we saw certainly in our analysis, so in the further analysis of the data, we looked inside the joint actually to try to determine where the force vector within the joint was acting. And we saw that for a small number of specific motions, it was deviating quite strongly towards the edge of the joint, but only in a few cases. And so if you were to look at maybe just an average walking pattern, you could agree with what's described in the standards for how a hip joint moves and is loaded. But if you would ignore these exceptional cases, I think in some cases it was, for example, doing a lunge or individual patients walking upstairs in a slightly different way, you would miss the fact that this loading vector is migrating towards the edge of the implant. And as you said, this edge loading is critical for the wear in these metal on metal hips, which has also been shown by other investigators. For example, in Lausanne, a group has shown this center pressure to edge distance is critical for wear as well.
So one of the kind of issues that we do have, I suppose, is that this enhanced testing or this additional testing would go for kind of increased simulator capacity. It takes typically 3 to 4 months to run 5 million cycle tests. And people in these days about doing 10 million cycle tests. So, effectively to one result or to one output is, will be or can be as long as kind of 6 to 8 months. Recently, the idea of computational preclinical trials has come to the fore as an adjunct to laboratory testing, where you can provide multiple simulations simultaneously and do kind of quite extensive parametric studies. I wonder what advantages or what challenges do you think that such an approach will have? And certainly your data could be used as input, couldn't it? Yours
Yep.
and Tony's data for that.
Exactly. I see a lot of potential, and quite often when I'm presenting our work, I draw some parallels to the automotive industry. That 20 years ago, if you want to prove the safety of a new car design, you had to build several prototypes and smash them into a wall with a huge amount of effort and expense to do that. And with the arrival of relatively cheap computational power and steady improvements in the simulation frameworks, probably 95% of crash testing is done on a computer with only one verification run at the end to prove that your final optimal design is the correct one. And in the Lifelong Joints project, I was really introduced to some fascinating work that was going on in collaboration between Leeds and Imperial College. I was familiar with wear simulation over the years, so computational models of the wear of two rubbing surfaces. But what was really coming through in the Lifelong Joints project is a further level of sophistication where the group, especially of Robert Hewson, they were looking at the development of the lubricating film within a joint and how this lubricating film is influenced by the load of the joint, and the presence or absence of that lubricating film therefore contributing to limiting or not being able to prevent wear in the joint. And so they developed a beautifully coupled lubrication wear model, which could quite accurately predict the very nonlinear progression of wear that's seen in experimental studies of prosthesis loading and wear. And this hasn't been captured in the past by the earlier, simpler simulation models. So having opened up that avenue to really be able to properly capture the physical process of lubrication and wear in a simulation model, and having created new methods to distribute this to parallel solving methods, for example, on graphical processing units, I think the doors are open now to be doing in silico preclinical trials in 95% of the work with only a limited number of physical experimental simulator runs required to verify and validate outcome. So I think we really are at the starting point of a new paradigm in terms of how we do the preclinical testing and evaluation of implant designs.
And I suppose there's two key points there. One is to have the population-based data sets, which you started to generate within, as you say, within Lifelong Joints, but also at the Charité, they've done some important work with kind of in vivo measurements. But also there's the kind of there's the relationships, isn't there, between load and wear and things
exactly
to be kind of teased out. So one of the kind of issues at the moment is that we still use this wear factor. Kind of rather than looking at the fundamental properties of the material. So that's really a challenge for us, is it, as engineers, to try and break away from that kind of single value and to do something more implicitly, around asperity contact, I suppose.
Exactly. And the beauty of the wear simulations for me is that, in contrast to an experimental measurement of wear, if you want to change the loading protocol that's applied to the joint, it's simply an input file that's modified. And in the case of a physical wear simulator, you may go beyond the capacity of the machine or the capabilities of the machine to do that. And you would have to physically reconfigure the machine to do some of these really odd and potentially deleterious loading patterns. So I think the simulation environment, the computer simulation environment, gives you a lot more options to explore a broader envelope of load conditions.
Absolutely. And it allows you, with these multiple and parallel simulations, to look at kind of the sensitivity of the outcomes to
correct
various inputs, which I think is kind of something that's missing from the kind of the physical simulator studies.
Exactly. And the nice thing that I see, again, looking back to the automotive industry, you can pinpoint the most critical loading conditions, which may then help you design better physical experiments to measure wear in the future. The same way that computer simulations of automotive accidents then led to an improvement of the physical crash tests that are carried out by the automotive industry.
going back a step, you mentioned kind of ortho load as being keyed in and a key stage in the evolution of joint loads and the availability of joint loads for for further experimentation. And they've kind of made a great resource in terms of the ortho website, and you can also access things like the equivalent joint motions as well. Is there going to be a similar sort of website or a similar sort of repository for the lifelong joints data?
That is our intention. So in different areas, we are making the data that was generated and the new methods that were generated in lifelong joints publicly available. So many of the kinematic data sets that came out of Tony Redmond's lab are publicly available, can be accessed. They have a DOI number associated with them, so they can also be cited. So other people could use these in their musculoskeletal simulation in the future. All the advances that we made to the musculoskeletal simulation model itself go back into a repository for the Anybody simulation framework. So anyone who reads our papers and is interested to either duplicate or advance our results has access to that repository, can download the models and use them as is or further extend them. So that was certainly, I think, one of the legacies of lifelong joints, is that the data and the analysis methods are for the most part publicly available.
Fantastic, fantastic. And finally, we're we're both involved in the BioTrib ITN, and I wonder where this kind of landscape, this kind of this advanced simulation fits into the kind of BioTrib framework.
I think there's a lot of different avenues. I can only speak mostly for the projects that we are planning to run at the ETH Zurich, and we see a huge value in what we did in lifelong joints to keep moving forward. So we have some projects that are looking at alternative biomaterials as bearing surfaces in the joint, with a view towards, in perhaps a decade's time, that we even have a semi-biological replacement for joints rather than purely synthetic replacements. So we are certainly going to take the loading protocols that came out of lifelong joints, and we're going to apply them to these new types of cartilage mimicking biomaterials to ensure that the performance under demanding loads is still adequate. And on the other hand, we're looking, and several other partners in BioTrib are looking at additive manufacturing as an avenue to create more complex and potentially more biomimetic joint replacements. And for sure, the motion and loading protocols that we determined in lifelong joints will flow directly into the design process for these additive manufactured devices that we are going to be coming up with. And then when it finally comes time to evaluate their performance, either in a computer or on a physical wear simulator, then our new devices are certainly going to be tested using protocols that were developed within lifelong joints. So I see a direct coupling between lifelong joints and the now starting BioTrib project. I think it's a really exciting propagation of results forward from one project into the next.
Okay, thank you very much. I think that concludes the kind of interview. That was kind of very interesting and very enlightening. And I just wish you well for your success in BioTrib. Thank you very much.
Thanks a lot. Pleasure to talk to you.
Thank you. Bye-bye.